The void is not empty. It is a tapestry of light.
Before we begin tonight, I want you to do something with me. Look up, or imagine looking up past your ceiling, past the atmosphere, past the moon, past the Sunday, past the edge of the solar system, past the nearest stars, past the Milky Way, into the space between galaxies, the Andromeda Galaxy. The nearest large galaxy to our own is 2.5 million light years away. 2.5 million light years, that is the distance that light, traveling at 300,000 kilometers per second, covers in 2.5 million years. If you started driving to Andromeda in a car at 100 kilometers per hour, you would arrive in approximately 26 quintillion years. 26 quintillion years, about 2 billion times the current age of the universe, and between us and Andromeda, almost nothing, just space. The intergalactic void, one of the largest and least understood environments in the cosmos, but almost nothing is not nothing. And tonight we are going there. Before we do, tell me where in the world you are right now. What country, what city, what time of night. I love knowing where these quiet, late night minds are gathering from. Drop it in the comments before you fall asleep. Now, let's go into the void. Opening cinematic. Imagine you could leave the Milky Way, not in a spacecraft with fuel and navigation. Just leave, step outside the galaxy, and look back. You would see a disk, roughly 100,000 light years across, bright in the center, where the stars crowd most densely around the supermassive black hole. That anchors everything, fading outward through spiral arms of stars and gas, to a dim, irregular periphery with the galaxy's halo of older stars and dark matter extends further still. You would see it the way you see any island from out at sea, distinct, bounded, finite, against the darkness, and then you would turn and look outward, away from the Milky Way, in any direction, and you would see darkness, not complete darkness, not perfect emptiness, but vast, enormous, profound darkness with very occasional lights, very far away. Other galaxies, some like ours, some different, some alone, some in small groups, some in enormous clusters, all separated from each other and from us by distances that make the Milky Way tiny. This is intergalactic space, the space between galaxies, the dominant environment of the universe, the place where most of the universe's volume resides, the place we understand least and which may hold some of the most important secrets in all of cosmology. What is intergalactic space? Defining the void, intergalactic space is the space between galaxies. This sounds simple, but pinning down exactly what it means requires some care. A galaxy is a gravitationally bound system of stars, gas, dust, and dark matter, held together by gravity, orbiting a common center. Our galaxy, the Milky Way, contains somewhere between 200 and 400 billion stars. Galaxies are surrounded by extended halos of older stars called the galactic halo, and by even more extended halos of dark matter that extend far beyond the visible disk. The edge of a galaxy is not a sharp boundary. It fades, the density of stars and gas decreasing gradually as you move outward until it is effectively indistinguishable from the intergalactic medium. So intergalactic space is more of a concept than a precise location. The space far enough from any galaxy that it is not significantly influenced by the gravity or the light or the gas outflows of any specific galaxy. The density of matter in intergalactic space, in the densest part of a galaxy, the interstellar medium, the gas between stars within a galaxy, has a density of perhaps 1 atom per cubic centimeter, already incredibly sparse by any everyday standard. In intergalactic space, the density drops by another factor of about 1 million, roughly 1 atom per cubic meter of space, 1 per cubic metre. To put that in perspective, the air you are breathing right now contains about 2.7 keres 2 quadradiquinte molecules per cubic metre, 27 septillion molecules per cubic metre in the air around you. Intergalactic space contains perhaps 1 atom per cubic metre, less than 1 trillionth of 1 trillionth of the density of the air. You're breathing, it is not empty, but it is very, very close. What that 1 atom per cubic meter actually is, the intergalactic medium is not made of the same stuff as most of the matter we're familiar with. It is not primarily hydrogen atoms. With electrons orbiting nuclei, it is primarily plasma, ionized gas, hydrogen nuclei, protons, and electrons separated, not in the form of neutral atoms, because the radiation from all the galaxies and quasars in the universe has ionized the intergalactic medium, stripped the electrons from the hydrogen atoms, leaving a hot, diffuse plasma of separate protons and electrons. This is called the warm-hot intergalactic medium. The WIM, warm-hot, is actually a significant understatement. The WIM has temperatures of roughly 100,000 to 10 million Kelvin, 100,000 to 10 million degrees Celsius. A plasma at 10 million degrees is what we normally call very hot, extremely hot, hot enough to fuse hydrogen in a star, hot enough to be at the core of the sunday. And yet it feels like it could be described as warm, because at those temperatures, the plasma emits mainly X-rays and extreme ultraviolet radiation, rather than the visible light or intense heat that we associate with fire or hot metal. The density is so low that despite the high temperature, there's very little energy. Per unit volume, a cubic meter of plasma at 10 million degrees, but with only 1 particle in it, contains far less heat energy than a cubic meter of air at room temperature that contains 27 septillion molecules. The temperature is high, the heat content is tiny. The scale of the void, numbers that cannot be felt. Let me try to make the scale of intergalactic space real to you, not just numbers, not just facts, but something that changes how you understand what the universe is. The Milky Way is approximately 100,000 light years across. That is the distance light travels in 100,000 years. The nearest galaxy, in terms of what we usually consider a galaxy of similar size, is the Andromeda Galaxy, M3+1, about 2.5 million light years away. The Andromeda Galaxy is 25 Milky Way diameters away, 25 times the width of our own galaxy of empty space between us and the nearest comparable island of stars to travel from the Milky Way to Andromeda at the speed of light would take 2.5 million years. At the speed of the fastest spacecraft we have ever built, the Parker Solar Probe, which reached about 635,000 kilometers per hour. At its fastest, the journey would take about 1.5 trillion years, about 100 times the current age of the universe, the local group, our galaxy, and the Andromeda Galaxy, and the Triangulum Galaxy, and about 50 smaller galaxies and dwarf galaxies are all gravitationally bound into a group called the local group. The local group extends over a volume of about 10 million light years, a sphere 10 million light years across, containing about 54 known galaxies. Outside the local group, the nearest major galaxy group or cluster is the Virgo cluster, the nearest large galaxy cluster, about 53 million light years away. 53 million light years of intergalactic space between the edge of our local group and the edge of the Virgo cluster, the observable universe. The observable universe, the region of space from which light has had time to reach us since the Big Bang, is approximately 93 billion light years in diameter. 93 billion light years in a universe that is only 13.8 billion years old. How can we see things 93 billion light years away if the universe is only 13.8 billion years old? Because the universe has been expanding. While the light was traveling, the objects whose light we are now receiving have moved much further away. Since that light was emitted, the expansion of space itself has carried them away from us. While their light was making the journey, the observable universe contains approximately 2 trillion galaxies. 2 trillion, 2 followed by 12 zeros. Galaxy, each one containing hundreds of billions to trillions of stars. And most of the universe, most of its volume, is the space between those galaxies, the intergalactic void, the whim, the cosmic emptiness that makes up the overwhelming majority of everything there is. A personal reflection. I find this one of the most disorienting and most calming things I know. Disorienting because the scale is so vast that my brain cannot hold it. I can write the numbers, I can manipulate them mathematically, but I cannot feel what 2.5 million light years means the way I can feel what 2.5 kilometers means when I know how long it takes to walk that distance, calming, because the problems that felt large before I started thinking about this feel smaller now, not insignificant. The things that matter to me still matter, but they sit differently in my mind against the backdrop of 93 billion light years of space most of which is void. There is something about the scale of the universe that produces a very particular kind of peace, not the peace of denial, not the peace of not caring, but the peace of perspective, of understanding that you are part of something so much larger than anything you were worried about. The cosmic web, the universe's skeleton, the universe is not randomly distributed. Galaxies are not scattered like dust evenly through the void. The universe has structure, large scale structure, the largest structures in the known universe that dwarf individual galaxies the way a continent dwarfs a city. This structure is called the cosmic web. What is the cosmic web? The cosmic web is the network of filaments and sheets and nodes and voids that organizes the matter of the universe. At the largest scales, imagine a vast three-dimensional spider web made of galaxies instead of silk. The strands of the web are filaments, long, thin structures where galaxies are densely concentrated, where gas flows from the surrounding void toward the dense nodes, where filaments intersect. At the nodes, where multiple filaments meet, are the galaxy clusters, the most massive, gravitationally bound structures in the universe, containing thousands of galaxies in a region only a few million light years across. Between the filaments and the nodes are the voids, enormous regions, nearly empty of galaxies that can span hundreds of millions of light years. How the cosmic web formed. The cosmic web was not designed or built in the way we build things. It grew from the quantum fluctuations of the early universe that we discussed in the physics episode in the very early universe. Fractions of a second after the Big Bang, the universe was almost perfectly smooth, almost perfectly uniform, but not quite. There were tiny variations in the density, quantum fluctuations, in the inflaton field, stretched to macroscopic scales by inflation. Regions that were slightly denser than average attracted matter gravitationally, growing denser over time. Regions that were slightly less dense lost matter to their denser neighbors, growing emptier. Over hundreds of millions of years, the slight density variations grew into the cosmic web. The originally slight density variations, amplified by gravity, into the dramatic structure we see today, dense filaments surrounding vast voids. This process is called gravitational collapse on cosmological scales, and it is one of the most well understood and most beautifully confirmed results in cosmology. The computer simulations of large-scale structure formation, called n-body simulations, run on supercomputers, start with the initial conditions determined from the cosmic microwave background and evolve the gravitational interactions of billions of simulated particles forward in time. The result matches what we observe with extraordinary precision. The simulated cosmic web looks like the observed cosmic web in every detail: the sizes of voids, the lengths of filaments, the masses of clusters, the distribution of galaxies. This is one of the great triumphs of modern cosmology that we can start from the quantum fluctuations in the early universe, apply the known laws of physics, run them forward 13.8 billion years on a supercomputer, and arrive at a universe that looks like the one we observe. The largest structures, the cosmic web, quantum structure, of truly staggering scale. The Hercules Corona Borealis Great Wall is a filament or superstructure of galaxy clusters that spans approximately 10 billion light years. 10 billion light years, about 1/10 of the diameter of the observable universe. It is so large that light traveling at maximum speed would take 10 billion years to cross it. It formed when the universe was younger than the time it would take light to cross it now, which creates its own puzzles for cosmologists about how such a large structure could have formed in the time available. The Sloan Great Wall, another enormous filament about 1.38 billion light years long, the CFA2 Great Wall, the Pisces-Cetus supercluster complex, the Shapley concentration, superstructures of galaxies and galaxy clusters that fill the cosmic web with structures that the human mind simply cannot visualize at the scale they actually are. The intergalactic medium, what fills the void? The intergalactic medium. The WIM is not uniformly distributed through the void. It concentrates in the filaments of the cosmic web, where it can be 10 to 100 times denser than in the voids. But even there, it remains extraordinarily sparse. By any everyday standard, the missing baryons problem. For decades, cosmologists faced a puzzle. They knew from the physics of Big Bang nucleosynthesis how much ordinary matter, baryonic matter, should exist in the universe. About 5% of the total energy mass content. But when they added up all the ordinary matter, they could find in stars, in galaxy, in the gas within galaxies, in galaxy clusters, in the gas around galaxies. They could only account for about half of the expected amount. Where was the other half? The missing baryons. The answer came from theoretical work and eventually from observations. The missing baryons were in the WHIM, in the warm, hot intergalactic medium, filling the cosmic web filaments, in the vast spaces between galaxies. The WIM, at temperatures of 100,000 to 10 million degrees, emits primarily X-rays and extreme ultraviolet radiation, not visible light, not the kinds of radiation that optical telescopes can easily detect. It requires X-ray telescopes or ultraviolet telescopes in space above Earth's absorbing atmosphere to observe, and even then, the density is so low that the signal is extremely faint, below the sensitivity of most instruments. But in the late 1990s and through the 2000s, the detection of the WIM improved dramatically with space observatories like Chandra and XMM Newton, and later others. Astronomers found the signature of the WHIM in the spectra of distant quasars, the light from quasars passing through the intergalactic filaments on its way to us. gets slightly absorbed by the ions in the WHIM, leaving specific, identifiable fingerprints in the spectrum, and gradually the missing baryons were found in the WHIM, confirming that the intergalactic medium contains a substantial fraction of all the ordinary matter in the universe, scattered in hot, dilute plasma through the cosmic web, invisible to optical telescopes, revealed only by X-rays and ultraviolet light. Galaxy clusters, the densest places in the web. At the nodes, where the cosmic web's filaments intersect, are the galaxy clusters, the most massive, gravitationally bound structures in the universe. A galaxy cluster can contain hundreds to thousands of galaxies, along with enormous amounts of hot gas and dark matter, all bound together by gravity in a region a few million light years across. The Virgo cluster, the nearest large cluster to the Milky Way, about 53 million light years away, contains more than 1,300 galaxies with a total mass of about 1.2 times 10 to the power of 15 solar masses, a quadrillion times the mass of the Sunday, and our own local group, our small collection of about 54 galaxies, is actually moving toward the Virgo cluster, falling inward very slowly at about 200 kilometers per second, drawn by its enormous gravity. Eventually, in billions of years, the local group will likely merge into the Virgo cluster, or what it has become by then, the Milky Way, will become one galaxy among thousands in a much larger structure. The intracluster medium, galaxy clusters, are not just collections of galaxies. They are filled with an even hotter, denser version of the WIM called the intracluster medium. The ICM, has temperatures of tens of millions to hundreds of millions of Kelvin, far hotter than the WHIM in the filaments, and it is visible in X-rays. The Coma cluster, one of the best studied galaxy clusters, about 320 million light years away, glows brightly in X-rays. From its intracluster medium, the hot gas between the galaxies, emitting X-radiation continuously. The mass of the ICM in a typical galaxy cluster is several times the mass of all the galaxies in the cluster combined. The gas between the galaxies is more massive than the galaxies themselves, and the dark matter that holds the cluster together is more massive still, typically about 10 times the mass of all the visible matter. Gas and stars combined, the cluster is mostly dark matter, with hot gas filling the space between galaxies, and the galaxies themselves being a relatively small fraction of the total mass. The visible parts, the actual galaxies that we can see with optical telescopes, are a minority of what is there. Galaxy cluster collisions, galaxy clusters sometimes collide with each other in one of the most dramatic events in the universe, the bullet cluster 10657-558, about 3.7 billion light years away, is one of the most famous galaxy cluster collision systems. It consists of two clusters that collided about 150 million years ago. From our frame of reference, the collision was so violent that the two clusters passed through each other. The hot gas of the two clusters interacted during the collision and was slowed down by electromagnetic interactions, lagging behind the galaxies themselves, which pass through each other without significant interaction. The result is a system where the hot gas visible in the X-rays is in a different location from the dark matter, which is detectable through gravitational lensing, the bending of light from more distant galaxies by the mass of the cluster. This separation of the gas from the dark matter is one of the strongest pieces of evidence for the existence of dark matter as a real physical substance rather than a modification of the laws of gravity. If there were no dark matter and the modified gravity theories were right, the gravitational mass should trace the gas, which is where most of the ordinary matter is concentrated. But in the bullet cluster, the gravitational mass traces the galaxies, not the gas, because the dark matter, which makes up most of the cluster mass, passed through the collision along with the galaxies without being slowed by electromagnetic interactions, because dark matter doesn't interact electromagnetically. The bullet cluster is a beautiful natural experiment that reveals the dark matter directly through its gravitational effect, separated from the ordinary matter by the collision, the cosmic voids, the emptiest places in the universe. Now let me take you to the other extreme. If galaxy clusters are the densest, most massive structures in the cosmic web, the voids are the opposite. Cosmic voids are the enormous regions between the filaments and sheets of the cosmic web, where the density of galaxies is much lower than average. Much lower. How much lower? A typical cosmic void has a galaxy density about 20% of the average. Some voids, the most extreme, have densities as low as 10% of average. The voids are not empty. There are galaxies in them, but far fewer than in the surrounding filaments. And the galaxies that are there tend to be smaller, less massive, less evolved than the galaxies in the dense filaments. The Boötes void, one of the most famous of the cosmic voids, is the Boötes void, discovered in 1981 by Robert Kirshner and his colleagues. The Boötes void is about 330 million light years in diameter. 330 million light years across a sphere, 330 million light years in diameter, nearly empty, of galaxies. When it was discovered, it was the largest known void in the universe. At that time, Robert Kirshner described the reaction of colleagues who heard about it as disbelief. The void seemed too large to be consistent with the standard models of how structure forms in the universe. It raised questions about whether the universe was as homogeneous as cosmologists believed at large scales. Since then, larger voids have been found. The KBC void, about 2 billion light years in diameter, is the largest known void, and we may be near its center. living in a void, the possibility that our galaxy might be in or near the center of a large cosmic void is not just interesting, it might have cosmological implications. If we are in a void, then the matter density around us is lower than the average of the universe, and the Hubble constant, the rate of expansion measured locally, might be slightly different. From the global value, there is, in fact, a tension in modern cosmology between the Hubble constant measured locally from observations of Cepheid variable stars and supernovae in our cosmic neighborhood, and the Hubble constant measured from the cosmic microwave background, which probes the early universe. The two measurements disagree by about 8 to 10%, a discrepancy called the Hubble tension that has resisted resolution despite many attempts. One potential explanation is the KBC void. If we are in a larger unnütze region, the local expansion rate might be slightly boosted compared to the global average by the outflow of matter from the void into the surrounding denser regions. This remains an open question, but it illustrates how the large-scale structure of the universe, our position within the cosmic web, may affect what we observe about the universe locally. Stray stars in the void, wanderers without a galaxy. In the dark spaces between galaxies, there are stars, not many, but they are there, wandering between the galaxies without belonging to any of them. These are called intracluster stars or intergalactic stars, depending on context, stars that have been stripped from their galaxies by tidal interactions with other galaxies or by the dynamics of galaxy cluster mergers, and that now drift through the intergalactic medium without attachment to any galaxy. How stars get ejected. When two galaxies pass close to each other or merge, the gravitational tidal forces can strip stars from the outer regions of both galaxies. These stripped stars form streams and shells around the merging galaxies. Some of them have enough velocity to escape the gravitational well of the merged system entirely and drift into intergalactic space. In galaxy clusters, where hundreds of galaxies are interacting gravitationally over billions of years, this process is even more effective. A significant fraction of all the stars in a galaxy cluster may be in the intracluster light, the diffuse, unattached population of stars between the cluster's galaxies. In some galaxy clusters, the intracluster light may contain 10 to 50% of all the stars in the cluster, a huge population of stars. Without galaxies, what life would be like around the star in intergalactic space if there were a planet around one of these wandering stars. What would the night sky look like from the Milky Way on a dark night? You can see a band of light across the sky. The galactic plane, thousands of individual stars with the naked eye, and many more. As a diffuse glow, the crowded arms of a galaxy from an intergalactic star that has been ejected into the void outside any galaxy the night sky would be very different. There would be no galactic band, no dense field of nearby stars. The sky would be mostly dark, with scattered across it tiny fuzzy patches of light, not stars, entire galaxies appearing as faint smudges in the darkness. The nearest individual stars would be tens of thousands or hundreds of thousands of light years away. In the nearest galaxy, which might appear as a faint, elongated smudge, the brightest thing in the sky, it would be a profoundly different experience of the cosmos, looking up and seeing not stars, but galaxy, the fundamental units of the universe, scattered across the sky, each one containing hundreds of billions of stars, but appearing as a single fuzzy dot. From that distance, this perspective would make the scale of things more immediately apparent than it is from the Milky Way, where the nearby stars fill the sky and distract from the vastness beyond, light traveling between galaxies. The ancient messengers, everything we know about intergalactic space, we know from light or from other forms of electromagnetic radiation, and from other messengers, neutrinos, cosmic rays, gravitational waves, light traveling between galaxies, tells us things that nothing else can. The redshift, as light travels through expanding space, its wavelength stretches the same way that the sound from an ambulance drops in pitch as it moves away from you. The Doppler effect applied to light causes recession to redshift, to shift light toward longer wavelengths, toward the red end of the spectrum. And because the universe is expanding, almost every galaxy beyond our local group is moving away from us. Carried by the expansion, the further a galaxy is, the faster it recedes, the more its light is redshifted by measuring the redshift of a galaxy's light. Astronomers can determine how fast it is receding, and from that, how far away it is. This is the fundamental tool of observational cosmology, the redshift survey, measuring the redshifts of hundreds of thousands or millions of galaxies, and building a three-dimensional map of the universe. The Sloan Digital Sky Survey, one of the largest astronomical surveys ever conducted, has measured the spectra and redshifts of more than 3 million galaxies and quasars, building the most detailed three-dimensional map of the nearby universe ever made. The cosmic web, revealed in unprecedented detail by the redshifts of millions of galaxies, absorption in the intergalactic medium. Light traveling between galaxies doesn't just redshift, it also gets absorbed partially by the gas in the intergalactic medium. Hydrogen gas in the intergalactic medium absorbs light at specific ultraviolet wavelengths, particularly the Lyman alpha transition at 10^26 nanometers. When a photon at exactly that wavelength passes through a cloud of neutral hydrogen, it gets absorbed, and as the universe expands, photons that started at shorter wavelengths are redshifted into the Lyman alpha wavelength at the point where they pass through the hydrogen. The result is a complex series of absorption lines in the spectrum of a distant quasar, one absorption line for each cloud of hydrogen along the line of sight at different distances and therefore at different redshifts. This is called the Lyman alpha forest because the spectrum is filled with dozens or hundreds of absorption lines from different hydrogen clouds at different distances, like trees in a forest, reading the Lyman alpha forest. The Lyman alpha forest is one of the most powerful tools in cosmology by analyzing the pattern of absorption in quasar spectra. Astronomers can learn about the distribution of hydrogen gas in the intergalactic medium along the line of sight at different cosmic epochs, the density and temperature of the intergalactic gas, the clustering of the gas, how it traces the cosmic web, how it changed over billions of years of cosmic history. All of this encoded in the pattern of absorption lines in the light from distant quasars, reading the intergalactic medium like a story written in absorption. In ancient light, the Lyman alpha forest also provides constraints on dark matter, specifically on whether dark matter is cold, moving slowly, or warm, moving faster. Cold dark matter and warm dark matter make different predictions for the small-scale structure of the intergalactic medium that are distinguishable in the Lyman alpha forest, magnetic fields in deep space, the hidden infrastructure. The intergalactic medium is not just gas and dark matter, it also contains magnetic fields everywhere in the universe, in planets, in stars, in galaxy clusters, and in the intergalactic medium between the clusters. Intergalactic magnetic fields are extraordinarily weak by everyday standards, perhaps a billionth of a Gauss, or even weaker. 1 Gauss is about the strength of a weak refrigerator magnet. A billionth of that is essentially unmeasurable in any laboratory on Earth, and yet they exist, and they have effects on the intergalactic medium that are detectable with the right instruments. How do we know they exist? The evidence for intergalactic magnetic fields comes from several sources. Rotation measure. When linearly polarized light passes through a magnetized plasma, the plane of polarization rotates by an amount that depends on the strength of the magnetic field and the density of the electrons along the line of sight. This is called Faraday rotation. By measuring the rotation of polarization of radio waves from distant radio galaxy passing through the intergalactic medium, astronomers can detect the integrated effect of the magnetic fields along the line of sight. The detection of Faraday rotation in the light from distant radio galaxy provides evidence for intergalactic magnetic fields with strengths on the order of a billionth of a Gauss, or perhaps somewhat stronger in the denser filaments of the cosmic web. the origin of intergalactic magnetic fields. Where do these fields come from? This is one of the genuinely unresolved questions. In cosmology, galaxies have magnetic fields generated by the dynamo mechanism, the interplay of turbulence and rotation inside the galaxy that amplifies seed magnetic fields into the strong fields. Observed, these galactic magnetic fields can be ejected into the intergalactic medium by supernova explosions and galactic winds and jets from active galactic nuclei, polluting the intergalactic medium with magnetic fields generated inside galaxies. But there is also the question of seed fields. What was the origin of the very first magnetic fields in the universe before galaxies formed, before any dynamo was operating? Was there a primordial cosmological magnetic field generated in the early universe, perhaps during inflation or during a phase transition in the hot early universe? Or were the seed fields tiny, generated by processes like the Biermann battery mechanism, which can generate weak magnetic fields in ionization fronts and shock waves in the early universe? The answer is genuinely uncertain. The origin of cosmic magnetic fields remains one of the open questions of cosmology, and the discovery of a truly primordial cosmological magnetic field would be one of the most important results in cosmology in decades. The observable universe and its edge, the limit of what we can see. Every time I think about the edge of the observable universe, I have to sit with it for a moment before continuing. The observable universe has an edge, not a physical edge, not a wall or a boundary or the end of space, but the horizon, the cosmic horizon. The edge of what we can observe is determined by the age of the universe and the speed of light. Light travels at a finite speed, 300,000 kilometers per second. In the time since the Big Bang, 13.8 billion years, light has had time to travel a certain distance to us from any source. Light from sources further than that distance has not had time to reach us yet. The observable universe is the sphere centered on us, from which light has had time to reach us since the Big Bang, but the universe has been expanding while that light was traveling. So the distance to the most distant things we can observe is not simply 13.8 billion light years. The expansion has stretched that to about 46 billion light years. The radius of the observable universe is approximately 46 billion light years. The diameter, about 93 billion light years. What is beyond the observable universe? We don't know. We genuinely don't know and cannot know with current technology or perhaps ever. But there are possibilities. The universe might be simply much larger than the observable universe. The total universe, including the unobservable parts, might be many times larger, perhaps infinitely larger. Inflation, the rapid expansion in the very early universe, would have made the total universe far larger than what we can observe. The observable universe would be a tiny patch of a much vaster whole. Beyond the observable horizon, the same physics applies, the same laws of nature, stars and galaxies, similar to what we see, probably filling the space beyond our horizon, or perhaps different physical constants in different regions if the multiverse is real and different bubble universes have different properties beyond our observable horizon, might be regions where physics is different, where atoms have different properties, where the forces have different strengths, and life, if it exists there, is completely different from anything we could imagine, or perhaps the universe beyond the horizon has the same physics, but is not infinite. Perhaps it is topologically closed, like the surface of a sphere, but in 3 dimensions, such that if you traveled far enough in one direction, you would come back to where you started, though the universe is so large that even if it is finite and closed, the topology would be undetectable. With current observations, the beyond is genuinely unknown and perhaps unknowable, which is one of the most profound and one of the most honest things physics has ever said. The universe from inside the void, a different perspective. Imagine you are inside one of the cosmic voids, far from any galaxy, far from any filament, in one of the emptiest places in the universe. What would you observe? What would the universe look like from there? The night sky, if you could breathe and look up, would be dark, profoundly dark, far darker than any night sky on Earth or even in deep space within a galaxy. There would be no Milky Way, no band of light from the densely packed stars of our galactic disk, no nearby stars of any kind. The nearest stars would be in the nearest galaxies, which would appear as faint, tiny, fuzzy patches tens of millions of light years away. The cosmic microwave background would still be there, the faint afterglow of the Big Bang filling all of space. Equally, in every direction, a faint, nearly uniform glow, too faint for human eyes, but detectable. With the right instruments, gravitational waves would still pass through from the mergers of black holes and neutron stars. Across the universe, ripples in space-time crossing the void at the speed of light, carrying the news of catastrophic events billions of light years away. Neutrinos produced in the nuclear reactions of stars in distant galaxy and in the remnants of the Big Bang. The cosmic neutrino background would still be passing through at nearly the speed of light in enormous numbers, but mostly there would be darkness and silence and the vast passion, emptiness of intergalactic space. And yet, the physics would be the same, the laws of nature unchanged. By the absence of nearby matter, an electron in the intergalactic void obeys the same quantum mechanics as an electron in your body right now. Quasars and active galactic nuclei, the brightest lights in the darkness. Between galaxies, the brightest objects in the universe shine quasars, quasi-stellar objects, the most luminous, persistent sources of energy known to exist. A quasar, at its peak, can outshine an entire galaxy of 400 billion stars by a factor of 100, 1,000, even more, from a distance of billions of light years. The host galaxy of the quasar is invisible, drowned in the brilliant light of the quasar itself. What is a quasar? A quasar is the active nucleus of a galaxy, the supermassive black hole. At the center is accreting matter at an extraordinary rate as matter falls into the accretion disk. Around the black hole, it accelerates, heats, friction convert, the gravitational energy of the infalling matter into heat and radiation. The inner part of the accretion disk reaches temperatures of hundreds of millions of degrees, emitting enormous amounts of radiation across the electromagnetic spectrum, from radio waves to X-rays. The energy conversion efficiency of a quasar is extraordinary. About 10 to 40% of the rest mass energy of the infalling material is converted to radiation. Compare this to nuclear fusion in a star, which converts about 0.7% of mass to energy. Quasars are 15 to 60 times more efficient as energy sources than nuclear fusion. Grain for grain, the most efficient known process for converting mass to energy in the universe. Quasars in the early universe, quasars, are mostly found at high redshifts. In the early universe, when the universe was young and galaxies were still forming, this is not surprising. A quasar requires a supermassive black hole that is actively accreting. In the early universe, the supermassive black holes were still growing, still filled by the abundant gas of the early galaxies, shining brilliantly as quasars. As the universe aged, the supply of gas for accretion in many galaxies declined. The supermassive black holes are still there. One sits at the center of the Milky Way, 4 million times the mass of the Sunday, and it is quietly, mostly dormant, not actively accreting, not shining as a quasar, just sitting there in the dark at the center of our galaxy, waiting. Quasars as probes of intergalactic space. The light from quasars, traveling billions of light years through the intergalactic medium to reach us, is the primary tool for studying the intergalactic medium. The Lyman alpha forest that we discussed earlier is observed in quasar spectra, the absorption of quasar light by intergalactic hydrogen. At different distances, the spectra of quasars are like archives of the intergalactic medium along the line of sight. Each absorption feature a record of gas at a specific redshift and therefore a specific cosmic epoch, a specific moment in the history of the universe. By studying the spectra of many quasars at different positions in the sky, astronomers can build a statistical picture of the intergalactic medium across the universe, how it evolved over billions of years, how the reionization of the early universe progressed, how the cosmic web developed, and how the voids grew over cosmic time, cosmic reionization, how the universe became transparent in the first 400,000 years. After the Big Bang, the universe was a hot, dense, opaque plasma. Light could not travel through it freely. The photons were constantly scattered by the free electrons. In the plasma, the universe was like a fog or a star's interior, opaque to radiation. Then, at about 380,000 years, the universe cooled to about 3000 Kelvin, cool enough for protons and electrons to combine into neutral hydrogen atoms. For the first time, when atoms formed, the free electrons were captured into the atoms and could no longer scatter the photons. The universe became transparent, suddenly, to radiation. This is the moment that the cosmic microwave background comes from the last scattering surface, the moment when photons were freed to travel freely. For the first time, those photons are the cosmic microwave background we detect today, stretched by 13.4 billion years of expansion from visible light to microwaves. After recombination, the universe was dark. Neutral hydrogen does not emit visible light. The first stars had not yet formed. There were no sources of visible radiation. This period is called the cosmic dark ages, hundreds of millions of years of darkness before the first stars formed and began to shine. The epoch of reionization, when the first stars and galaxies formed around 200 to 400 million years after the Big Bang, they began emitting ultraviolet radiation that ionized the surrounding neutral hydrogen. Bubbles of ionized gas grew around the first stars and galaxies and expanded over hundreds of millions of years until the bubbles overlapped and the intergalactic medium was completely reionized. The universe was returned to an ionized state by the radiation of the first cosmic structures. This is the epoch of reionization occurring roughly between 200 million and 1 billion years after the Big Bang. Understanding reionization is one of the great frontiers of observational cosmology. When exactly did it happen? What drove it? Galaxies, quasars, something else? How did the bubbles of ionized gas grow and merge? The James Webb Space Telescope, launched in 2021 and currently in operation, is specifically designed to look at this epoch, to observe the first galaxies that reionized the universe, to study the very beginning of the cosmic web, when the first structures were lighting up the dark universe. For the first time, the future of intergalactic space, where the void is going. Intergalactic space is not static, it is changing, driven by the expansion of the universe and by the accelerating expansion driven by dark energy. Right now, galaxies that are not gravitationally bound to the local group are receding from us, carried by the expansion in the future, the acceleration of the expansion driven by dark energy. If it continues, will cause an increasing number of galaxies to recede faster than the speed of light, not through space, but because the space between us and them is expanding faster than light can cross it. These galaxies will become permanently invisible to us. Their light will never reach us. They will pass beyond our cosmic horizon for good in about 150 billion years. If current trends continue, the observable universe from the Milky Way's perspective will shrink to the Milky Way and the Andromeda Galaxy, which will have merged into one large elliptical galaxy. By then, all the other galaxies, all 2 trillion of them, will be gone beyond the horizon, moving away faster than light can follow forever. An astronomer living in the Milky Way 150 billion years from now would look out and see only their own galaxy, the merged Andromeda, and nothing else, all the other galaxies gone from view. They would not know that trillions of galaxies existed beyond their horizon because no signal from those galaxies could ever reach them. They might conclude that their galaxy was the entire universe, that there was nothing else. They would be wrong, but they would have no way of knowing. We are fortunate to live at a time early enough in the universe's history that we can still see the 2 trillion galaxies of the observable universe and piece together the story of how it all began and how it is structured, the cosmic web, the voids, the clusters, the filaments, all visible to those who look. The philosophy of the void, what intergalactic space teaches us. I want to sit with the philosophy before we close the first part of our journey into intergalactic space. The void, the cosmic void, is not nothing. It is a specific kind of something, a very diffuse, very hot, magnetically threaded, expanding something that makes up most of the volume of the universe. And it teaches something important about the nature of emptiness. Humans tend to think of emptiness as the absence of things, as nothing, but physics says otherwise. The void between galaxies contain gas and magnetic fields and quantum fluctuations of the vacuum and gravitational waves passing through, and neutrinos and dark matter, and the cosmic microwave background, radiation, and the possibility of life, though vanishingly unlikely, around the wandering stars. In the void, there is no true nothing. In the universe, even the emptiest space is full of quantum fields vibrating at their 0-point energy, full of virtual particles appearing and disappearing, full of the ghost-like presence of every force and every field that fills the universe. Uniformly, the void is not empty. The void is the background against which everything else happens. It is the stage not the absence of the play. And we who live on planets, around stars, in galaxy, in the dense, bright, structured parts of the cosmic web are the exception, not the rule. Most of the universe, by volume, is the void. We are the strange minority, living in the dense, bright, structured places. The void is the universe's default state, and we briefly, locally, are its most improbable, most complex, most self-aware exception. Let your breathing slow, let the scale of intergalactic space settle around you like the void itself, vast, patient, not empty, but close, the cosmic web stretching across 93 billion light years, the voids, hundreds of millions of light years across the clusters at the nodes, the filaments threading between them, the whim at 10 million degrees, between the galaxies, the wandering stars, drifting through the darkness without attachment to any galaxy. And you here in a galaxy at a specific location in the cosmic web near the edge of a spiral arm of a medium-sized galaxy in a small group of galaxy on the edge of a supercluster in the universe that is mostly void. The void is not frightening. It is the most peaceful place there is. Quiet, vast, old, indifferent, and in its indifference, strangely comforting. Rest now. The void will still be there. When you wake, before we continue tonight, I want you to do something again. Look up, or imagine looking up past your ceiling, past the atmosphere, past everything. You know more now than when we began. You know that the space between galaxies is not truly empty. You know, it is filled with the warm, hot intergalactic medium, plasma at millions of degrees. You know, it is threaded with magnetic fields so weak that no instrument on Earth could detect them directly. You know, it is crossed continuously by neutrinos and gravitational waves and the faint glow of the cosmic microwave background. You know that the universe has a skeleton, the cosmic web, filaments and nodes and voids, the largest structure that has ever existed. You know that quasars, the brightest objects in the observable universe, shine across billions of light years of intergalactic space, carrying in their light a record of everything the void contains. And you know that we are the exception, not the rule, that the universe is mostly void and we live in the dense, structured, improbable minority of it. Tonight, we go further. We're going to look at some of the phenomena we didn't have time for in the first part, the mysteries that remain open, the detections that changed everything, the future of intergalactic space, and what all of this means for something as small as a single human life lying somewhere in the world at this hour, listening. So breathe slowly. Let the images settle, the filaments, the voids, the wandering stars, the ancient quasar light. Let it all settle. And let's go back out into the dark between everything the James Webb Space Telescope, the machine that sees the beginning. In December 2021, a rocket launched from the Guyana Space Center in French Guiana, carrying something that had taken 30 years and $10 billion to build the James Webb Space Telescope. Webb traveled for a month to its operating position 1,000,000 miles from Earth at the second Lagrange point, where the gravity of the Earth and Sunday balance, allowing it to orbit. The Sunday in sync with Earth, it unfolded itself over 2 weeks, a mirror 6.5 meters across, made of 18 hexagonal, gold-coated segments of beryllium and a sun shield the size of a tennis court, folded origami style for launch, unfolded in space with extraordinary precision, because a single failure would have ended the mission that could not be repaired, like Hubble, 1,000,000 miles from any human hands. Why infrared? Webb sees in infrared light, not visible light, like Hubble, because the universe is expanding the light from the most distant galaxies, the ones formed just a few 100 million years after the Big Bang, has been stretched by the expansion of space from ultraviolet and visible wavelengths to infrared. To see the first galaxies, you need an infrared telescope. Webb was built specifically to see back to the epoch of reionization, to observe the first sources of light in the universe that began to ionize the intergalactic medium and end the cosmic dark ages. What Webb has found in its first years of operation, Webb has already transformed our understanding of the early universe, and specifically of the intergalactic medium and the epoch of reionization. Webb has observed galaxies from when the universe was only a few 100 million years old. Light that has been traveling for over 13 billion years to reach us. And some of what it found was surprising, even to the people who built it. The galaxies in the early universe are more massive, more structured, more evolved than many models predicted. They should be at that epoch, galaxies that look like mature spiral galaxy, existing when the universe was less than 1 billion years old, when the models suggested only chaotic, irregular, early-stage galaxies should exist. This doesn't mean the models are wrong in any fundamental sense. It means they need to be refined, adjusted, improved to account for what Webb is actually seeing. This is how science works. New observations challenge existing models. The models are updated, understanding improves. Webb has also observed the spectra of galaxies from the epoch of reionization and seen the signatures of ionizing radiation, the ultraviolet photon escaping from these early galaxies into the surrounding intergalactic medium, ionizing the neutral hydrogen, bubbles of ionized gas growing around the first galaxies. As models predicted, but now seen directly, for the first time, the epoch of reionization is no longer just a theoretical construct based on indirect evidence. Webb has shown us what it looked like, what it actually looked like when the universe was first being illuminated, galaxy by galaxy, bubble by bubble, the cosmic dark ages ending in the light of the first structures, fast radio bursts, the most mysterious signals in the universe. In 2007, a radio astronomer named Duncan Lorimer was searching through archival data from the Parkes radio telescope in Australia, looking for pulsars, the rapidly spinning, dense remnants of dead stars that emit regular pulses of radio waves. He found something that wasn't a pulsar, a single burst of radio waves, lasting only a few milliseconds, but extraordinarily bright and with a characteristic called dispersion that told him the signal had traveled through a large amount of plasma before reaching Earth, so much plasma that it could only have come from outside the Milky Way. The signal was so brief, so bright, and apparently so distant that it didn't fit any known category of astronomical source. This was the first fast radio burst, 3B, now called the Lorimer burst. At first, many astronomers were skeptical. Perhaps it was interference, a microwave oven in the observatory kitchen. It had happened before. Radio telescopes sometimes pick up terrestrial interference. That mimics astronomical signals, but more bursts were found in other data sets by other telescopes. In other parts of the world, the signals were real, astronomical, extragalactic, and completely mysterious. What a fast radio bursts. FRBs are extremely brief, intense bursts of radio waves, lasting from a fraction of a millisecond to a few seconds, originating from cosmological distances billions of light years away. In those few milliseconds, an FRB releases as much energy in radio waves as the sun releases in a year or more from a source far smaller than a solar system. The dispersion of the signal, the fact that lower frequency radio waves arrive slightly later than higher frequency ones because they travel more slowly through the plasma of the intergalactic medium, tells us how much plasma the signal has passed through, and therefore roughly how far away the source is. Most FRBs appear to come from hundreds of millions to billions of light years away. The intergalactic medium that the signal crosses leaves its mark in the dispersion of the burst, encoding in the arrival time difference between different wavelengths, a record of every electron the signal encountered on its journey, the source of FRBs, the discovery of repeating FRBs, bursts from the same location multiple times, ruled out cataclysmic one-time events like two neutron stars merging for at least some FRBs, the leading hypothesis for at least the repeating FRBs is magnetars, neutron stars with extraordinarily strong magnetic fields, a billion times stronger than any magnet built on Earth, and about 1,000 times stronger than a typical neutron star. Magnetars are known to produce sporadic, intense bursts of X-ray and radio energy when the stress in their magnetic fields exceeds a threshold, and a sudden catastrophic rearrangement of the field occurs. In April 2020, a magnetar in our own Milky Way, Skria 1935-2154, produced a burst of radio waves that was detected by radio telescopes and was consistent with what a distant FRB would look like if it had occurred in another galaxy. This was the first direct evidence that magnetars could produce FRBs, not conclusive proof, not the only possible source, but strong evidence for one mechanism, FRBs as probes of intergalactic space. Whatever their source, FRBs are extraordinary tools for studying the intergalactic medium. Every FRB that reaches us has traveled through billions of light years of the intergalactic medium and carries encoded in its dispersion, in its polarization, in the details of its spectrum, a record of everything it encountered on that journey by measuring the dispersion measures of many FRBs. At known distances, astronomers can map the distribution of electrons in the intergalactic medium, average the electron density along many lines of sight, build a statistical picture of the whim across the universe. FRBs have already been used to detect the missing baryons, the matter, in the warm, hot intergalactic medium that the Lyman alpha forest had struggled to account for in every detail by using the dispersion measures of localized FRBs. Astronomers confirmed that the total electron density in the intergalactic medium matches the expected density of the missing baryons, a direct detection of the whim through FRBs. In the future, with many more FRBs detected and precisely localized, FRBs may become one of the primary tools for mapping the intergalactic medium in 3 dimensions, probing the distribution of gas in the cosmic web filaments, measuring the magnetic fields of the intergalactic medium through the Faraday rotation of the burst polarization, and testing models of large-scale structure formation with a precision not previously achievable. The universe sends us signals from billions of light years away, lasting milliseconds, carrying information about everything they pass through. On the way, we are just beginning to learn how to read them. The dipolar anisotrope, we are not at rest. There is something peculiar about the cosmic microwave background when you look at it very carefully. The CMB, the ancient light of the early universe, is almost perfectly uniform in every direction, the same temperature to within about 1 part in 100,000 everywhere in the sky. Almost there is one large-scale pattern in the CMB that stands out, a dipolar anisotrope. One side of the sky is very slightly warmer. The other side very slightly cooler, by about 1 part in 1,000, far larger than the tiny 1 in 100,000 fluctuation that seeded the cosmic web. This dipole is not cosmological. It is caused by our motion. The Milky Way is moving through the universe at about 600 kilometers per second toward a point in the constellation Leo. The Doppler effect blue shifts the CMB slightly in the direction we are moving, and red shifts it in the direction we are coming from. 600 kilometers per second is fast by any everyday standard, but it has several components that reveal something about our place in the cosmic web. Our solar system is orbiting the center of the Milky Way at about 220 kilometers per second. The Milky Way within the local group is moving at about 80 kilometers per second toward the Andromeda Galaxy, and the local group as a whole is moving toward the center of the Virgo cluster at about 200 kilometers per second, but the Virgo cluster itself is moving towards something even larger, the Shapley concentration, the densest concentration of galaxy clusters in the observable universe, about 650 million light years away, containing hundreds of individual clusters. The pull of the Shapley concentration on the Virgo cluster, on the local group, on the Milky Way, on the Earth, on you is real and measurable. You are right now being accelerated gravitationally toward a mass concentration 650 million light years away. You are moving relative to the CMB at 600 kilometers per second in a specific direction toward Leo. You are not at rest in the universe. Nothing is. Everything is moving through the cosmic web, drawn by the gravitational pull of the structures around it. This motion through the void is the universe doing what it always does. Gravity working patiently over billions of years, drawing matter toward density, emptying the voids, further filling the clusters. More, the Sunyaev-Zeldovich effect reading clusters in the CMB. There is a remarkable way that galaxy clusters leave their mark on the cosmic microwave background called the Sunyaev-Zeldovich effect, or the SZ effect, named for the Russian astrophysicists Rashid Sunyaev and Yakov Zeldovich, who predicted it in 1969, when CMB photons, the ancient light of the early universe, pass through a galaxy cluster. They interact with the hot electrons of the intracluster medium. The hot electrons at temperatures of tens of millions of degrees scatter the CMB photons. By inverse Compton scattering, the photon gain energy from the electrons during the scattering and shift to slightly higher energies, slightly shorter wavelengths. The result in the direction of a galaxy cluster. The CMB appears slightly cooler at low frequencies and slightly warmer at high frequencies, a spectral distortion that is the unmistakable signature of the cluster. The SZ effect is extraordinary as a tool because it does not depend on distance. An object twice as far away appears 4 times dimmer in ordinary light, but the SZ effect is independent of distance. A cluster at 10 billion light years produces the same SZ signal as an identical cluster at 1 billion light years. This makes the SZ effect an ideal way to fit and characterize galaxy clusters at all redshifts, at all distance, back to the earliest epochs, when clusters were first forming. The South Pole Telescope and the Atacama Cosmology Telescope have used the SZ effect to discover hundreds of galaxy clusters, including clusters at high redshifts that are already surprisingly massive for their age, challenging and refining our models of structure formation. The SZ effect is also one of the tools being used to search for the warm-hot intergalactic medium in the filaments of the cosmic web between clusters. The filaments contain hot gas, not as hot as the intercluster medium, but hot enough to produce a detectable SZ signal if you average the CMB along the direction of many filaments, cross-correlating the CMB maps from the Planck satellite with the positions of known galaxy pairs and looking for an SZ signal in the direction of the filaments connecting them, has detected the filamentary gas in the cosmic web directly, an indirect detection, but a real one, the hot gas in the filaments of the cosmic web, imprinting itself on the ancient light of the Big Bang as that light passes through on its way to us. The universe writes its structure into its own light, and we learn to read it. Gravitational lensing, space as a lens, intergalactic space, contient masse, dark matter, hot gas, galaxy, galaxy clusters, and all of this mass curves space-time as Einstein's general relativity predicted when light from a distant source passes through or near a massive concentration of matter. The curved spacetime bends the light's path like a lens. This is gravitational lensing, and it is one of the most powerful tools in cosmology for probing the matter distribution of intergalactic space. Strong lensing when a massive galaxy or galaxy cluster lies almost exactly between us and a distant galaxy. The lensing can be so strong that the distant galaxy appears as multiple images, or a ring called an Einstein ring, or as spectacular arcs of light stretched and distorted around the lensing mass. The Hubble Space Telescope and now Webb have produced some of the most beautiful images in all of astronomy, from strong gravitational lensing, galaxy clusters surrounded by blue arcs, stretched and distorted images of distant background galaxies magnified by the enormous gravitational mass of the cluster. Strong lensing doesn't just produce beautiful images. It tells us about the mass distribution of the lensing cluster, including the dark matter. By modeling the positions and shapes of the arch, astronomers can reconstruct the total mass distribution of the cluster in great detail, seeing the dark matter through its effect on light that it bends but does not absorb or emit, weak lensing when a massive structure is not perfectly aligned with a background source. The lensing effect is weaker, not multiple image, not arch, but a subtle distortion of the shapes of background galaxies, a slight stretching in a preferred direction too small to see in a single galaxy, but detectable when you average over millions of background galaxies. This is weak gravitational lensing, and it is one of the most powerful proofs of large-scale structure currently available by measuring the statistical alignment of shapes of hundreds of millions of galaxies across the sky. Astronomers can map the distribution of mass in the intervening large-scale structure, including the dark matter in the filaments of the cosmic web. The Dark Energy Survey, the Hypersuprime-Can survey, and upcoming surveys like the Rubin Observatory's Legacy Survey of Space and Time, ELSIST, are using or will use weak lensing from hundreds of millions of galaxies to map the cosmic web in unprecedented detail, testing models of dark matter, dark energy, and the growth of large-scale structure across billions of years of cosmic history, microlensing at an even smaller scale when a compact mass, a star or a brown dwarf or a black hole, passes in front of a background star. It acts as a lens, temporarily magnifying the background star. A microlensing event, microlensing, has been used to search for dark matter candidates in the form of massive compact objects, machos, black holes, brown dwarfs, neutron stars, wandering through the halo of the Milky Way or through intergalactic space. The results have ruled out machos of most masses as the primary form of dark matter. Dark matter is not primarily made of failed stars or rogue black holes. It must be something else, something more exotic, something we have not yet directly detected. Lensing of the CMB, even the cosmic microwave background, the ancient light of the early universe, is gravitationally lensed by the large-scale structure it passes through on its way to us. Over 13.4 billion years of travel, the CMB is a nearly perfect, uniform background source. Any distortion of its pattern can be attributed to gravitational lensing by the intervening large-scale structure. The Planck satellite and ground-based CMB experiments have measured this lensing in detail, extracting a map of the integrated mass distribution along the line of sight to the last scattering surface, including the dark matter in the cosmic web across billions of light years. The universe is full of natural lenses, made of mass, revealing to us the matter we cannot see by the way it bends, the light that we can intergalactic cosmic rays, messengers from catastrophe. The universe is not quiet, even in the void, high energy particles called cosmic rays, mostly protons, and atomic nuclei, and electrons accelerated to extraordinary energies, travel through the intergalactic medium at close to the speed of light. Some cosmic rays are produced within the Milky Way by supernova remnants and pulsar wind nebulae and other energetic astrophysical sources. But the highest energy cosmic rays, the ultra-high energy cosmic rays, Uherkris, with energies far beyond anything a particle accelerator can produce, must come from outside the Milky Way, from extragalactic sources, somewhere in or beyond the cosmic web, the GCK limit. There is a theoretical limit to how far an ultra-high energy cosmic ray can travel through the universe, called the Greisen-Zatsepin-Kuzmin limit, the Gatz-K limit, calculated independently by Greisen and by Zatsepin and Kuzmin in 1966. Ultra-high energy protons traveling through the universe interact with the photons of the cosmic microwave background, producing pions and losing energy. In the process, this limits how far a proton with the highest observed energies can travel, to about 160 million light years. Beyond that distance, the proton would have lost too much energy to arrive. With the energy we observe, the Gatz-K limit means that the sources of the highest energy cosmic rays must be within about 160 million light years of Earth, within our local corner of the cosmic web. Finding those sources is one of the goals of the Pierre Auger Observatory in Argentina and the telescope array in Utah, the largest cosmic ray detectors ever built, covering thousands of square kilometers, detecting the showers of secondary particles produced when ultra-high energy cosmic rays hit the atmosphere. So far, the sources of the highest energy cosmic rays have not been conclusively identified. Possible candidates include active galactic nuclei and gamma ray bursts and magnetars, and the shock waves of galaxy cluster mergers, all environments where particles could be accelerated to the extraordinary energies observed. The intergalactic medium through which these cosmic rays travel also affects them. The magnetic fields of the intergalactic medium deflect the paths of charged particles, bending their trajectories, making it harder to trace them back to their sources. Ultra-high energy cosmic rays, heavy nuclei, rather than protons, are deflected more because they have higher charge and lose energy faster through interactions with the CMB. The detailed properties of the intergalactic magnetic field, its strength and coherence length determine how much cosmic rays are deflected, and therefore how well we can use them to identify their sources, measuring the arrival directions of cosmic rays and correlating them with known astrophysical sources, constraints, the intergalactic magnetic field, another way of probing the void through the messengers. It sends us the missing satellite problem and what it tells us about dark matter, the cosmic web predicted by our standard model of cosmology, cold dark matter with a cosmological constant, lambda CDM, makes specific predictions about the number of substructures within galaxies and within galaxy groups. Dark matter halos should contain smaller subhalos. Within them, the Milky Way's dark matter halo should contain hundreds to thousands of smaller subhalos, each potentially hosting a dwarf galaxy. But when astronomers count the known dwarf galaxies around the Milky Way, there are only about 50, far fewer than the hundreds to thousands of subhosts. Predicted, this discrepancy is called the missing satellite problem, and it has been one of the most active areas of research in cosmology. For 2 decades, several explanations have been proposed and explored. The first is baryonic feedback, the effects of stars and supernova, and the radiation from new stars on the gas in small dark matter halos. Small halos have shallow gravitational wells that the energy from supernova explosions and stellar winds can blow the gas out of. Without the gas, and without the gas, no starsform, and without stars, no visible dwarf galaxy, even though the dark matter halo is still there. Invisible, this is called reionization feedback and supernova feedback, and it may resolve much of the missing satellite problem. High resolution hydrodynamical simulation that include these baryonic processes produce a number of satellite galaxies more consistent with what is observed. The second is that the nature of dark matter itself might be different from what the cold dark matter model assumes. If dark matter is not perfectly cold, if the dark matter particles have some small velocity in the early universe, warm dark matter rather than cold dark matter, then the small scale structure would be suppressed. Fewer small halos would form naturally. Courte observation of the Lyman alpha forest and of the number of dwarf satellites constrain how warm dark matter can be, and the constraints suggest dark matter must be close to cold. But some intermediate scenario remains possible. The third is that the predictions of the number of subhalos were made without adequate treatment of the baryonic physics, and that with better simulations, the predictions and the observations will agree. Recent progress has moved in this direction. The gap between predicted and observed satellite numbers has narrowed significantly as simulations have improved. the missing satellite problem may be on its way to resolution through better understanding of how gas and stars and supernovae affect the small-scale structure of the cosmic web, the intergalactic medium and star formation. The web feeds the galaxies. The intergalactic medium is not just a passive backdrop to the galaxies that live within the cosmic web. It is an active participant in the life of galaxies. Galaxies need gas to form stars. Stars are made of gas, mainly hydrogen, that collapses under gravity into dense clouds and eventually into the hot cores where nuclear fusion ignites. But galaxies are continuously consuming their gas, converting it into stars. Stars that live and return some gas to the interstellar medium of the galaxy, but often enriched with heavier elements and not necessarily returned at the same rate. It is consumed. Where does the fresh gas come from? The intergalactic medium, the cosmic web. Gas flows along the filaments of the cosmic web toward the galaxies at the nodes in two modes: hot mode accretion in massive galaxies and galaxy clusters. The infalling gas passes through a shock wave at the boundary of the galaxy's halo and is heated to the virial temperature of the halo, millions of degrees, before it can fall further into the galaxy. This hot gas must cool radiatively before it can collapse into clouds and form stars. Cooling is slow in massive halos, and the supply of cold gas to the galaxy is limited. Cold mode accretion in smaller galaxies. The infalling gas doesn't pass through a virial hook. It flows in cold, along cold streams, threading through the hot halo directly to the galaxy, much more efficiently, feeding star formation at higher rates. This cold mode of gas accretion along cold streams of the cosmic web may be responsible for the high star formation rates observed in Galaxies. In the early universe, when the filaments were denser and the cold streams more vigorous, the Lyman alpha blobs, some of the most remarkable objects discovered in deep imaging surveys of the distant universe, are enormous glowing clouds of hydrogen-gas, tens to hundreds of thousands of light years across, called Lyman alpha blobs. These blobs glow with the emission of excited hydrogen atoms, emitting the Lyman alpha photon. When an electron falls from the second to the first energy level, the source of the exciting energy in Lyman alpha blobs is debated. It may come from cold accretion streams from the cosmic web, releasing gravitational energy as gas falls in along the filaments, illuminating the surrounding hydrogen in a spectacular nebular glow. Lyman alpha blobs may be the direct observational signature of cosmic web filaments feeding early galaxies with cold gas, glowing in the energy released by that feeding Mare Visible to our telescopes. In this interpretation, the most dramatic, glowing objects in the distant universe are not powered by starbursts or quasars, but by the gravitational energy of the cosmic web itself, the web glowing as it feeds the first galaxies, the void galaxies, life on the frontier, within the cosmic voids, the nearly empty regions between the filaments of the cosmic web. There are galaxies, not many, but they are there, and they are remarkable. Void galaxies are among the most isolated objects in the universe, separated from the nearest major galaxy by tens of millions of light years of almost empty space. They are also among the least evolved, the most pristine in their properties, unaffected by the environmental processes that transform cluster galaxies. Ram pressure stripping, tidal interactions, galaxy mergers, harassment by neighboring galaxies, void galaxies are often actively forming stars, blue, irregular, rich in gas, the raw material for star formation, having had none of it, stripped away by the hot intracluster medium, in some ways void galaxies. Maybe the closest analogs to the primitive early galaxies of the young universe, evolving slowly in their isolation, undisturbed by the rush of environmental processes that dominate in the dense regions. The Void Galaxy Survey has studied many void galaxies in detail, finding that they are indeed structurally distinct from galaxies of similar mass in denser environments, more often late type, more often blue and star-forming, more gas-rich, more likely to be irregular or to show signs of recent unimpeded star formation. They are, in a sense, the survivors of the early universe, living out in the frontier of the cosmic web, evolving in peace, not transformed by the turbulent social environment of clusters, intergalactic neutrinos, the ghost particles. Everything we have discussed so far involves electromagnetic radiation, photon, radio waves, X-rays, gamma rays, light in all its forms. The universe speaking to us through the one messenger, our instrument. We're first designed to receive, but the universe speaks in other voices to neutrinos, or particles with almost no mass and no electric charge that interact only via the weak nuclear force and gravity, not electromagnetism, which means they pass through almost everything without interaction. A light year of solid lead would stop about half of the neutrinos passing through it, which means that for all practical purposes, neutrinos are invisible to ordinary matter, and yet they carry important information about the universe and in particular about intergalactic space and its most violent events, the cosmic neutrino background. Just as the cosmic microwave background is the relic radiation of the early universe. There is a cosmic neutrino background, the relic neutrinos of the Big Bang, produced in the first second when the universe was hot enough for neutrinos to be in thermal equilibrium with everything else, and then decoupled when the universe cooled and the density fell low enough that neutrino interactions became negligible. These relic neutrinos are everywhere in the universe, filling all of space, about 340 per cubic centimeter, 100 from each of three flavors of neutrino and antineutrino. They are not directly detected. Their energy is far too low for any current instrument, but they influence the large-scale structure of the universe. Their small but non-zero mass affects the growth of structure in ways that leave a measurable imprint on the cosmic microwave background. And on galaxy surveys, the mass of neutrinos is constrained by cosmological observations of large-scale structure, one of the few cases where cosmology provides tighter constraints than particle physics experiments. High-energy neutrinos. In 2013, the IceCube Neutrino Observatory, buried in the Antarctic ice sheet, a cubic kilometer of ice instrumented with 5,160 detectors, announced the detection of neutrinos from outside the solar system, high-energy astrophysical neutrinos, not from the Sunday, not from Earth's atmosphere, but from somewhere else. The energies of these neutrinos range from a few TeV tera-electron volts to several PV beta-electron volts, energies more than 1,000,000 times higher than any man-made particle accelerator can produce. They come from all directions in the sky, suggesting multiple extragalactic sources, active galactic nuclei, galaxy clusters, star-forming galaxies, all have been proposed as possible contributors in 2022. IceCube reported the first statistically significant association of high-energy neutrinos with a specific astronomical source, the active galaxy NGC 1068, also known as Messier 77, about 47 million light-years away, in the constellation Cetus, a Seyfert galaxy with an active supermassive black hole at its center, surrounded by dense gas and dust, neutrinos from a supermassive black hole, 47 million light-years away, crossing the intergalactic void and arriving in a cubic kilometer of Antarctic ice, where they occasionally interacted and were detected. The void does not stop them. Nothing does. They cross billions of light years of the universe. Like the universe isn't there, gravitational waves from deep space, ripples across the void, the detection of gravitational waves. Beligo, in September 2015, was one of the most profound scientific achievements of the 21st century, predicted by Einstein's general relativity. In 1916, they were not directly detected. For 100 years, because the technology required to detect them was so extraordinarily precise that it took decades of development to build it. Gravitational waves are ripples in space-time itself, produced by accelerating masses, specifically masses accelerating asymmetrically. The most powerful sources are the mergers of compact objects, black holes, neutron stars, or combinations in a binary black hole merger, two black holes orbiting each other, spiraling together over millions of years as they radiate gravitational energy, eventually merge in a fraction of a second, releasing a burst of gravitational radiation with a power that briefly exceeds the combined luminosity of all the stars in the observable universe. In electromagnetic radiation, these gravitational waves travel through the intergalactic medium at the speed of light. Unimpeded by anything, gravitational waves do not interact with matter in any way that diminishes them, unlike electromagnetic radiation, which can be absorbed, scattered, blocked by intervening matter. Gravitational waves pass through everything, the entire intergalactic medium, as if it weren't there. LIGO and Virgo have detected dozens of gravitational wave events, binary black hole mergers, binary neutron star mergers, and likely black hole neutron star mergers, all from hundreds of millions to billions of light years away. Each detection is a record of one of the most violent events in the universe, compressed into a few seconds of signal in the detector after crossing the intergalactic void completely unimpeded. The neutron star merger 2770817, detected in August 2017, was particularly remarkable because it was detected simultaneously in gravitational waves by LIGO and Virgo, and in gamma rays by the Fermi and Integral space telescopes, and then in visible light, ultraviolet, X-rays, radio, as the kilonova, the explosion produced by the merging neutron stars, was observed from hundreds of telescopes around the world. This was the birth of multi-messenger astronomy, the same event seen in gravitational waves. Neutrinos had been searched for but not detected. From this event and across the electromagnetic spectrum, the same event, speaking in different voices, carrying different information about what happened, the void transmitted all of these messengers over 130 million light years, gravitational waves, gamma rays, visible light, all crossing the intergalactic medium together in the speed of light, race to our detectors. The gravitational waves arrived about 1.7 seconds before the gamma rays, consistent with both traveling at the speed of light but confirming with the highest precision ever achieved that gravitational waves do travel at the speed of light as general relativity predicts, and confirming that the difference in arrival time must be dueto, the slightly different emission times or emission locations of the two signals within the merger event, not the dueto, any different speed. What intergalactic space teaches us about ourselves, the perspective of the void. We are almost at the end of this journey into the space between galaxies. I want to stop and sit with what this all means, not just as physics, not just as cosmology, but as something that changes how you see yourself and your life and what matters. The void is the universe's default state, 93 billion light years of space with 2 trillion galaxies scattered through it. And most of the volume is void. We live in one of the rarest, most improbably, most structured places in the universe, a planet around a star, inside a galaxy, in a galaxy group, on the edge of a supercluster, in a filament of the cosmic web. We live in the exception, not the rule. The rule is plasma at millions of degrees, 1 atom per cubic meter. Magnetic fields too weak to measure in any laboratory the occasional passage of a cosmic ray or a neutrino or a gravitational wave from something catastrophic billions of light years away. And against that backdrop of profound, patient, ancien, emptiness, here we are, not just matter, not just energy, not just particles, obeying the laws of physics, but matter organized to the degree that it can look out at the void and ask what it is that it can build instruments to detect a neutrino from 47 million light years away that can map the cosmic web from surveys of hundreds of millions of galaxies that can hear gravitational waves from merging black holes 1 billion light years distant. This is not common in the universe. This may be extraordinarily rare. Every neutrino that passes through you right now, from the Sunday, 100 billion per square centimeter per second passes through the Earth and continues into the intergalactic void and will cross the local group and approach the Virgo cluster and enter the larger intergalactic medium and travel for billions of years until it is eventually absorbed somewhere or just keeps going. In the endless expansion, you are right now part of the intergalactic medium. In a sense, the neutrinos passing through you are treating you as barely distinguishable from the void. The gravitational waves passing through stretch and compress you by less than 1,000th of the diameter of a proton, but they do. They stretch you. The void passes through us. We are part of its medium, the philosophical void. What emptiness really is, there is a concept in many philosophical traditions of emptiness as something more than the absence of things, as a kind of presence in itself. Physics has something to say about this, not because physics is philosophy, but because physics has discovered that emptiness is indeed something, the quantum vacuum, the emptiest state of the universe, is not nothing. It is a state of minimum energy, not zero energy. The uncertainty principle prevents exactly zero energy. The vacuum fluctuatis, the vacuum is alive in a quantum sense, with virtual particles appearing and disappearing, with fields vibrating at their 0-point energies. The Casimir effect, real, measurable, is caused by the quantum fluctuations of the electromagnetic field in the vacuum between two plates, the Lamb shift. Real, measured, is caused by the quantum fluctuations of the electromagnetic field. In the vacuum around the hydrogen atom, the vacuum has structure, has energy, has fluctuation, has effects, and the intergalactic void is not the quantum vacuum. It is filled with plasma and magnetic fields and radiation and dark matter and dark energy and gravitational waves and neutrinos and the ancient light of the Big Bang. The void is not nothing. It never was. There is no nothing in physics, and this, I think, is one of the most profound things that physics has discovered about the universe. There is no nothing, even the emptiest, most isolated region of space is something, has properties, obeys laws, participates in the universe. Nothing is not available in this universe, only emptier or fuller version of something. Where are we in the web? Our cosmic address, let me tell you where you are right now in the cosmic web, precisely as we know. You are on Earth, third planet of our solar system, built from the remnants of earlier stellar generations. 4.5 billion years old, the solar system orbits the center of the Milky Way at about 26,000 light years from the galactic center in the inner part of the Orion arm, one of the minor spiral arms of the galaxy. The Milky Way is the largest galaxy of the local group, along with Andromeda, our nearest large neighbor, 2.5 million light years away, and about 54 known galaxies of various sizes. The local group is located near the outskirts of the Virgo supercluster, a large concentration of galaxies and galaxy groups centered on the Virgo cluster. About 53 million light years away, the Virgo supercluster is itself part of a much larger supercluster complex, Laniakea, 500 million light years across, containing about 100,000 galaxies and 100 million billion solar masses of material. The local group is near the edge of Laniakea, on the edge of one of its filamentary arms. Laniakea is embedded in a region of the cosmic web that may be within or near a large underdense void, the KBC void, about 2 billion light years across. We may be cosmic suburbanites living near the edge of our supercluster, on the edge of a large void in the cosmic web. This is our address in the universe, Earth, Solar System, Orion Arm, Milky Way Galaxy, Local Group, Virgo Supercluster, Laniakea Supercluster Complex, KBC Void Region, Observable Universe. Each level of that address contains thousands or millions or billions of the level below it, and at each level, the void, the empty space between the named structures dominates by volume. We are a specific, unique, local arrangement of matter at the smallest level of the address in a universe that is mostly the absence of such arrangements, the future of the web and our place in it, where the void is heading. We touched in the first part on the future of intergalactic space under the influence of dark energy and the accelerating expansion. Let me fill in some of the details. The fate of the local group, the Milky Way, and the Andromeda Galaxy are approaching each other at about 110 kilometers per second. They will merge in roughly 4.5 billion years, a collision that will play out over 1 billion years of back and forth before the two galaxies settle into a single large elliptical galaxy, sometimes called Andromeda. The other members of the local group will be absorbed or will settle into the gravitational well of the merged galaxy. The local group, as a bound structure, will survive the dark energy, because the dark energy drives galaxies apart only on scales where gravity is too weak to hold them together. For the local group, the mutual gravity of the Milky Way and Andromeda and the other members is strong enough to hold the group together against the cosmological expansion. But the rest of the universe, the Virgo cluster, and everything beyond it will continue to recede, driven by dark energy, faster and faster over the coming billions of years. The Virgo cluster is about 53 million light years away right now, and we are moving toward it at about 200 kilometers per second. But the expansion of space is moving it away. Faster, we will never reach it. The expansion wins on longer time scales. The observable universe, from our perspective, will shrink as more and more galaxies cross our cosmic horizon, receding too fast for their light to ever reach us. In about 2 trillion years, the only things visible from the merged Andromeda galaxy will be the stars and galaxy remnants of the local group. Everything beyond will be gone, dark, invisible, out of contact forever. A civilization living then would have no way of knowing that the universe had ever been different, that 2 trillion galaxies had once been visible, that the cosmic web had once been mappable, that the CMB had once been detectable in the direction of the last scattering surface. We live in the golden age of cosmology, when all of this is still visible, still mappable, when the evidence for the cosmic web and the voids and the clusters is accessible. If you look And some of us have looked and have found a universe more strange, more beautiful, more structured, more empty, more full than anything the humans who first looked up at the night sky could have imagined. The closing, what the void offers you. We are at the end of this journey, from the room you're in, past the atmosphere, past the moon, past the Sunday, past the edge of the solar system, past the nearest stars, past the Milky Way, into the intergalactic void, into the warm, hot intergalactic medium, plasma at millions of degrees, 1 atom per cubic meter, threaded by magnetic fields, too weak to measure. In any laboratory, crossed by fast radio bursts, carrying the news of catastrophic events billions of light years away, crossed by neutrinos from active black holes, crossed by gravitational waves from merging neutron stars, crossed by the ancient photons of the cosmic microwave background, which started their journey 380,000 years after the Big Bang and are still traveling, still filling all of space, equally in every direction, including this room right now and the cosmic web spanning the observable universe, filaments hundreds of millions of light years long, nodes where thousands of galaxies accumulate, voids where almost nothing exists for hundreds of millions of light years in every direction, and the void galaxies drifting in the emptiness, blue and star forming, isolated, undisturbed for billions of years, and the wandering stars stripped from the galaxies, drifting through the dark between the islands of stars with their night skies of galaxies. Instead of stars, all of it real, happening now, right now, while you lie here and breathe and let your thoughts slow. The void is not nothing. The void is not frightening. The void is the context in which everything exists. The vast, patient, ancien, mostly empty, but never quite empty, background against which stars and galaxies and life and minds are the extraordinary, improbable, brief, local exception. You are one of those exceptions right now in this room, on this planet, around this star, in this galaxy, in this local group, in this supercluster, in this region of the cosmic web and the void, all of it, all 93 billion light years of it, the 2 trillion galaxies, the trillions of stars in each galaxy, the warm hot plasma between them, the dark matter threading through, the dark energy pushing it all apart. All of it is your context, your address, your home in the most literal, physical sense. You are not separate from this. You are in it, made of it, part of it, the rarest part, the most structured part, the most briefly conscious part, the part that looks out and asks, what is all of this? And the void says nothing. The void is not the kind of thing that speaks, but what we've built, the telescopes, the detectors, the theories, the simulations, the generations of careful patient, brilliant human beings that devoted themselves to the question. They have given us an answer, not complete, not final, but real and verified and extraordinary. This is what all of this is: a cosmic web of filaments and voids built from the quantum fluctuations of the first fraction of a second, expanded by dark energy, scaffolded by dark matter, lit by galaxies and quasars, and the faint, ancient glow of the Big Bang itself. And in one small galaxy, in one small group, on one small planet, around one ordinary star, for one brief cosmic moment, something figured it out. A little that something is you, and everyone else who looked up and kept looking. Let that be enough. For tonight, let your breathing slow. Let the void settle around you, vast and patient and real. The void will still be there when you wake up, exactly as large, exactly as patient, exactly as full of everything it contains, and it contains far more than nothing it always did. Rest now. The intergalactic medium is not going anywhere. The cosmic web will wait. The ancient photon of the CMB are crossing this room right now and will continue long after you sleep. And wake and go about your ordinary, extraordinary day. Sleep well. The void is peaceful. It always was.